Hello, everybody. This is going to be a quick video on data races and race conditions. So let's just dig right in. First of all, these are very related terms. One of them is a very technical term, like multiple threads. Sometimes we'll talk about tasks or processes in this class, threads sort of along those lines. Access the same data where at least one is right. So it's multiple, threads or tasks or whatever, accessing data, the same data, and at least one is right. A race condition is very related to this. And that is the correctness of your program based on the sequence or timing of multiple threads. Again, tasks, processes, whatever you want to call them. And so this one is just sort of a technical situation of like what is happening. And this is like, oh, my program is broken, crashing, whatever. It's important to note that neither is a subset of the other. And let's talk about that really quickly. So those are those two definitions I was talking about, where the data race is just, things are accessing multiple threads accessing the same data, and at least one is right. Race condition is basically, is your program still correct based on how it plays out? And if we talk about that really quickly, there's a lot of different output data races. There are data races and race conditions. That's sort of like the most common scenario. It is definitely a huge problem in parallel programming. I would almost go so far as to say it is the problem in parallel programming. You can't have this benign data race where there's technically a data race, two tasks are accessing the same data location, at least one is a right, and it's okay. And I'll show off a kind of silly example of that today. There are some other races called, amongst other things, determinacy races and atomicity races, which we'll cover later in the semester. So let's just talk about a couple of data races. The first one is, I want you to imagine like no join. If you look at this program, we create some data, we void fork that data, we assign it to 231 and then print it out. And if you look at the computation graph over here, like how this data race, how this code plays out, this is a race condition and a data race. This task over here is reading the data when it's printing, reading data sub 0 when it's printing it out. And this one is writing it out. And so how the output of this program, what the program will output is whether or not this write happens before the read. And so it can either print 0 or 231. So let's go really quickly over to Eclipse. And when I run this program, you can see it's printing 0. I bet if I run this a bunch, it'll print 0 a heck of a lot. Because basically what you're saying is this fork, can it get like the entire parallel system up and run and like launch this task and get the 231 in before we move on to print? Now, if I ran this 100 million times, it would eventually produce the 231. And there are other things where this would happen, where it happened much more frequently. Even if you run it a million times, it's like, this is never going to happen. That's still a bug in your program. It could definitely happen, and you certainly don't want to build a pacemaker with it. And this is, again, like obviously the most simple program I can possibly make. Don't take these examples as, sort of like how pernicious a problem this thing is. This is just sort of the simplest program I could come up with that has a database. Let's talk about another one. This one is going to be also very simple. In this one, I make an array that is one long. I fork a task that assigns that location data sub 0 to be 231. I assign another task to be, then the continuation goes ahead and sets it to 425. I join, right? And then I print out what it is. There's a data race between these two tasks, the continuation and the fork task. Each of them assigns or writes to this data location. What the program will happen is whoever's last will win. So if I come over here and look at Eclipse again, and let's look at same location data race, I can see 231 won that time. I run it again. It's like 231 a lot. And what that means, it took a while there. I've actually run this enough so that 425 will print. And that's just kind of a sort of thing that can happen where what's happening is this, it makes sense that, this is, again, a sort of a little bit related to the fact that this is going to be the first task we make. And we're bringing up the whole parallel system to do that. But this guy takes a while to actually, be scheduled. This guy happens right away. And so 425 gets written, the join happens, which waits for this guy to complete. So this guy is coming up last a lot. Again, if you ran it a ton, you could get a situation where it would print 425 instead. All right, so let's move on again. I want to talk about just how small a window this sort of thing is. plus plus is not atomic. So in this program, I again have one piece of data, and I am incrementing it here and incrementing it there. And you can sort of see again, now we're both reading and writing the data. If I move on and show like what this looks like at sort of the Java virtual machine level, or most programs, like at the lowest level, you can imagine this reads in data sub-zero into some register, it increments it, and then writes the data, that register, back out to this data location. So you can either think of it as this way, where they're both reading and writing, like plus plus increments, like reads from the location, increments, and writes it out. You can sort of think of it in this sort of broken down stance. And again, I'm going to come over here and run this program, the plus plus data race, and it's going to print out 2 a lot. Again, these are the simplest possible programs, where like there's so little time going here. It's sort of not, it's always exhibiting 2. I will show in a future video, we'll do this a ton, and you'll sort of see how this can be a problem. And so back over to our sort of more examples. This is the benign data race, and this is kind of the exception that proves the rule, kind of crazy. To imagine I make a piece of data, an array that's 1 long, I assign it to 42 in this task, right? And then the continuation also assigns it to 42, right? And I join and I print it out. This is always going to produce 42, which makes sense. This is still technically a data race, right? Because 2 tasks or 2 threads are accessing the same data. At least one of them are right. Both of them are right. But it's not a race condition, because both, no matter how you run it, it will always produce 42. And so this is in this sort of very sliver of this. Benign data races aren't the norm. We actually have a less contrived example in this class coming soon, which has a benign data race. They're not unheard of, but sort of the big problem is usually in this section. And I can run this real quick, and we'll just see it go to 42, as you might imagine, with both of them assigning it to 42. This one I can run 100 million times. It will always be 42. Let's move on to a couple of other things. The real key here is that, like, we don't have to make data races. There's a couple of things. This is a correct program. It has no race condition or data race. And in this solution, I've made it so there's 2 slots, 1 for each. And this data is written out to 231. I've written a slightly different program where one of them assigns 231. That's its work. The other one assigns 425. I join it, so that's safe, right? And then I print down here, no 2 tasks are reading and writing from the same location at the same time. And so everything's good. So I can sort of run this program really quickly right here, correct different locations. And you can see it's always going to produce 656 because there's no data race, and everything is good. Now, the last one I'm going to say is like, we're going to use void fork, and we're going to mutate shared data in this class. And it's not like it's totally without use, like it definitely has its uses. I will say that a lot of times, there's nothing wrong with making your program functional, and then it's really hard to make a data race. Like, it's hard to forget to join if your future is sort of requiring it. So this is the same program I have here with the void fork, where I'm like mutating this shared data. In this case, I'm not mutating shared data ever. Like, this future returns 231. This one assigns B to 425. I join it, so this guy completes, and then I add A plus B. And that one also always produces the correct answer. And so we can run this 100 million times also. So hopefully that makes sense, and is a brief introduction to what a data race is, what a race condition is, and also, rather importantly, how to avoid them a little bit.